get into things first. Erlang distribution, we heard about it. Great thing. Actually, that's the thing that attracted me to Erlang. I needed to build a distributed system, and I heard about this programming language was built in distribution, and that was the first thing that attracted me. I stayed for the fault tolerance and for the increased productivity, but well, distribution is still important to me. It is, I don't need to explain that here, transparent connection of Erlang nodes. There's two ways to do it. Basically with the naming, you can have short names and long names. That's more for a crowd that doesn't know that much about it. And let's look at a thing that actually happens by default. Let me shrink this. So if I run, which three things do I take? Foo, a node foo, and a node bar. Is this readable? Bigger? Bars. So let me try to get it bigger. I hope it doesn't overlap now. Go awake nodes. Okay, so this is two distributed nodes which are not connected to each other, so it's actually not so good. No, this way. So from the last one, I actually, let's connect it to foo at my machine name, and also let it connect it to bar at my machine name. So now we have connections from the lower window to the other two. So so that's the neighbors this node sees, but if I look here, then we see that the bar node also has a connection to the foo node, because the net kernel makes a fully connected mesh. So we get a triangle. We didn't connect these two nodes, they're connected by themselves. That, of course, back to the slides. There can be an issue. It used to be a scalability problem. Historically, there was something about 70 to 200 nodes that you could run, depending on who you talk to. It's probably more by now, because the hardware got more beefy and etc. But it's more about like failing links and the fully connected mesh not always being available. I heard from WhatsApp that, somebody from WhatsApp correct me if the numbers are wrong, that they have 10K nodes which they run in an almost fully connected mesh. So they don't rely on it to be fully connected, but that actually kind of works. So it's actually not as bad. But you don't always want a fully connected mesh, so there are remedies. The newer one is connect all false. If you start your node with that, if I would have done this on these three machines, they wouldn't have done this cross connection. They only do the connection that you tell it. And before there was a feature called hidden nodes, which are nodes kind of like are hidden from this whole machinery of fully connected mesh building. And so you can have outliers. They're still very useful to kind of like hook into something without suddenly everything connecting to your laptop. But it's kind of like the connect all false is the thing that we are actually using. Yeah, there's another thing. There's security. Not really. There's this cookie, which is more a feature that you don't by accident connect to the wrong cluster, but it's no security at all, basically. And it actually says so in the documentation. But actually there is security, because you only need to connect your Erlang nodes with TLS. Easy. Just encrypt everything and authenticate and have public key. And the only thing that you need now, and the only is in big quotes, is a PKI. I've been hearing this sentence for 25 years. It's like, yeah, public key solves everything. You only need a PKI. Everybody who knows about PKIs, and yeah, this is a gnarly problem. And it's not an only problem. So let's take this away. Can we switch to the other screen, please? And let me show you the first thing, how easy it could be to run actually Erlang nodes, planet scale, distributed. Is it readable? Yeah, okay. All over the world. So what Luca is doing here, we're deploying here the infrastructure. This is on Flight.io in Amsterdam, in Toronto, in Singapore, in Miami, in Frankfurt, in Stockholm, Arlanda. It's Erlang codes I learned today. In, I forgot this one. The other one is Bogota. This is somewhere in Iowa or something. It's somewhere in the US. So 8 nodes. We are starting this as our infrastructure, and we want to deploy to these locations on the planet in a secure network, because you don't want to have open Erlang distribution on the internet. So deploying Braid across 8 regions. We can go on. So now this is our infrastructure. This is kind of like where we actually want to push stuff to. Oh, waiting for instances. So that's the slow part. That used to be faster. Now we have BraidNet is ready. So now what we do is we deploy a ring, which is a config file, basically, which describes a graph. So what this does is you can describe an arbitrary graph of nodes in a config file, but we prepared a few config files ahead of time, and this one is a ring with 8 nodes, and we run this Docker container there, which is also on the Erlang Docker container, basically, running on release. And what we see here, that's kind of like the config file content, that's the graph. It looks a bit gnarly because it has this weird host names there. We need to improve that, but we will do this all in graphical way. So let's go on. So now this is running, but kind of like it's a little bit like looking at this config file is not so nice. So we actually made a nice visualization, which we integrated into our. Well, it's not integrated yet because this is on a special version of it on the IoT thing. So that's actually this ring of nodes. And here we can see node, stupid jacket at long hash, region Frankfurt, if you can't read it. Then it's the orange one is in Bogota, the red one is in Miami, etc. So let's send some messages. So we did a simple ring traverse, so basically a little server that basically sends it to the next node in the ring. And actually, there's a wait of 2 seconds in there, because if you let it run on full speed, you can't see anything. It just zooms around the planet like this, and it's pretty much at light speed. So kind of like every node, when they get the message, they show this little label. So this message is going around the planet now on an encrypted, TLS encrypted, authenticated node of a network of Erlang nodes in a ring. And let's do some other topologies. Hypercube. So Hypercube is an extension of a cube. It's an interesting structure of high-performance computing. They like hypercubes because you kind of like get lots of nodes. The node grow with exponentially, but the links per node don't grow exponentially. So that is a 4-dimensional hypercube. So we have 16 nodes and 4 links per node. But the maximum distance in the network is 4 also. So that's a nice property. And we have some hypercube travel, so we kind of like travel around the message with the hypercube. So now we try to get from 0 to 1, 1, 1, kind of like to the other corner. And it kind of like collects it past where it was. This again running on 8 regions, so you see the colors are the regions basically. So these are the nodes that we spun up on these regions. And we did some random travel also. And then we go on with the slides. So now it jumps around in the hypercube. Again, TLS connected everywhere. And did you see us setting up a PKI? No, because that's hidden from you. You don't have to do it. We do it for you. And how this works, I'm going to explain. Can we switch back to the slides, please? So what does Braid do for you? It takes care of the distribution over TLS. all the TLS setup, which is not that easy, is taken away. It just works. It manages all the keys and certificates. Sorry. It allows arbitrary topologies, so you can basically make a config file, make you a weird graph topology, whatever you want. But of course, there's a few simple ones that probably everybody wants. It goes planet scale, you have seen it. And there's an interesting extra feature that your application actually doesn't even get hold of the private key, because we hide it in the orchestrator. We learned that doing IoT security, when you have the key in a secure element, we use basically the orchestrator as a secure element for the container. So we actually added a hook to TLS, which is going into OTP 27, where we kind of like when the setup, the link setup happens, and it needs to sign the nonce of the other side, then actually this calls out to the orchestrator, it does the sign and gives back the signature without ever sharing the public key. So if your application doesn't have the public key, not the public key, the private key, if your application doesn't have the private key, you can't lose it. More security. So how does it look? Very simple. That's how it works actually. I probably won't explain everything. There is basically on every host server, basically in this case like location, we have a BraidNet instance, which is the orchestrator, the local part of the orchestrator. And here we have actually multiple Docker containers started. So you remember we had multiple with the same color. So there's multiple Docker containers started on this host server, which has a little thing Braid node, which you need to add to your application. So it actually makes this all work magically. And then you add your own release in there. And that's all. So everything is in Braid node. There's a client machine where you control everything. And that is basically the root of the PKI, where the certificates come from. So actually not that hard. It just looks a bit complicated. So this port mapping and TLS signing, so we kind of like hook into EPMD and into TLS. So kind of like to make all this work that the nodes find each other, we kind of like hook into port mapper and tweak it a bit. So they actually gets the right port in the right instance by going to the BraidNet instance and then going into the container that it actually needs to be. And the TLS handshake, when it happens, basically this please sign thing goes to the orchestrator and is not done in the actual container. So that's the parts. That is all open source. The integration and the visualization is not open source, that it will be part of our IoT platform. But we open source as much as possible of all our components of everything. So we run this. The demo was running on Fly.io. Just kind of like short explanation what it is. It's an edge cloud. So it provides you lots of locations very close to your customers. So you get short latency to the edge or to actually IoT devices or whatever you're running there. It is very spread out. It has a kind of like peculiarity that you actually provide a Docker container to run, but they unpack it into a machine. And they have some routing magic that I can't explain right now. If you want to know how that works, talk to me later. That you have one IP, and it always makes sure that it connects to the closest machine in their network by magic, well, routing magic. And it's actually built with Elixir, and that's why that's the only reason I mention it here, because it's actually they're one of us, and they use our stuff. It's still growing, and it has some growing pains still. So it could be very interesting. So in order to provide all these Docker containers where we need Erlang VMs in there, we provided a very little plugin for Rebar, which was actually quite simple to write, but nobody did it before for surprising reasons. It just takes your Erlang release and sticks in a Docker container with the Erlang VM. That's it. You just use this and run it, and then you get a container. Nothing to do. And we have this in our second demo, which we switch over to now. So now we change the code and actually deploy the thing, so you see that this is not just a fake video. Well, it could be two fake videos, but That would have been too much work. So what we do is basically we reduce the timeout, like the delay that we added, that it's actually visible from 2 seconds to half a second. So it should be running, zooming around faster now. And now, that scrolled away. So that, what Luca was running was Rebus 3 Docker deploy, I think, that used the plugin, and that created the Docker container, and it's done. Yeah, this Rebus 3 Docker build and Docker push to Docker Hub. So we basically use Docker Hub we push the container on Docker Hub because that's where the current Braid pulls it from. So now this is already deployed. No, not yet. Sorry. Yeah, deploy nodes. So now we deployed the new code, planet-wide. I still find this fascinating, honestly. And now it should be running faster. Let's see if it works. Is it running faster? Yeah, it's running faster. Okay, that was the second demo. So back to the slides. So next steps, well, we want to make it even more seamless, especially with graphical tools that you just like click on the nodes that you want to deploy to and everything. And also kind of like make it safer to use, because that's one of the things on Fly. You can actually lose a lot of money on Fly if you're not careful. Because it's not like that you say you can just spin up 50 machines and then you need to call Amazon again and say, please, I want more. Well, they'll let you do what you want. You get what you pay for, or you pay for what you did before. So we try to make it a little bit more safe, maybe, make a nicer visualization, and we want to not only have this running on the cloud, but we want to mix it basically from cloud to edge, and I'm getting to that. And also, we want to make it work. Oh, where's the other clouds? I think there's another slide here. So future extensions, we have these GRiSP boards that some of you might have seen. They're in boxes on our booth. Currently, we are building GRiSP Nano, which is an even smaller GRiSP board. And here we have the cloud stuff with the thing, and we want to connect this together, basically. So that you, and deploy Erlang releases down into these very small nodes here, from the cloud to the edge, because we are building a thing where we automatically place the computation where it needs to be. But this will be another talk. And we also don't want to kind of like, we want to make this multi-cloud because this would be just a driver module to actually make the other clouds work. I mean, it's a bit of work. Kind of like talk to all this cloud. So you can actually do multi-cloud stuff. And a little bit about GRiSP. No, we don't have time for that. And I talked about it before. We do new PMODs. That's just a quick update. We do hardware. We actually have a battery, which we just need to test for the GRiSP. That's the important thing. I mentioned GRiSP Nano. So if we look at the diagram, cost, size, power, speed, which is about the same, then GRiSP 2 is kind of like here somewhere in the middle field. If you want to look at the Raspberry Pi, the graph is too small because the power usage is up there for a normal Raspberry Pi. But what we want to do is basically we want to kind of like see how close we can get to the origin. And because we are working this in an energy harvesting project, we want to go power the lowest, basically, the most low-powered Erlang node that ever existed. And when I say Erlang node, I don't mean a reduced VM, but a full VM. Because we want to run the same code here and there without having to think about VMs. Communication will be ultra-wideband, less PMOD connectors, etc. So that would be, and that will be tied together in this platform. I still have 5 minutes, okay, I can actually talk about the platform. So what I wanted to say before, this is kind of like getting out of this way that we do IoT applications now, that you build some C code to run in a small IoT node, and then maybe, I don't know, whatever, make some C++ code to run in the gateway or Python, and then do something else in the cloud. And then you need to invent protocols between all these nodes. And then when you figure out like, oh, actually this code should not be running in a gateway, but on the small node or in the cloud or whatever, then it's a lot of work to change. You have a very rigid system. Or if you say, oh, I need more computation at the edge and I want to sit a server in the corner, to integrate the server is a big development project. So what we want to build, and what we are currently building for years now, is you develop your distributed application that runs from cloud to edge, and state your user intent. Like here, I need low latency, I need high bandwidth, this thing uses a lot of energy, and then also describe your heterogeneous network. For example, this is an energy harvesting node that doesn't have much energy. You can't do a lot of compute there. This has little bandwidth, this has lots of bandwidth, here's the latency high, and then we automatically map, at first statically, and later on dynamically, the computation to where it needs to be. So this will not only work for Erlang, but it will work better for Erlang. For obvious reasons, because we have the actual write once, run anywhere that Java promised back in the days. It works much better with us, because we can actually go into the small things without kind of like reducing the language and everything. And the Braid thing that you saw today, this is the orchestrator that we use for all of this, or will be using. That's the basis. On this platform, there will be freebies for GRiSP 2 owners. So anybody bought the GRiSP 2 board, you will be getting something free, because you can hook up your GRiSP board to the IoT platform for free and look at the logs and do some monitoring. Currently, only the logs work, but that was the thing that annoyed me most with my GRiSP boards, that I never know when it crashed what happened. Yeah, you saw this screen already. And we are opening public beta today. So come to our booth. So that is for disclaimers. The Braid stuff, most of the Braid development was done under the Teraflow project, funded by the EU, and continued by the Rescale project, also funded by the EU. In Rescale, by the way, we can work a lot on supply chain security, especially for Erlang, because we are the Erlang partner there. So this will be, we will be getting good things out for the Erlang ecosystem out of this second project. For sure. And that is my last slide. We even have time for one question, probably.
Yes, please. Thank you, Per. And we do have time for a question. And we have a question over here.
How does the node authenticate to the orchestrator if it doesn't have a private key from the beginning?
The orchestrator spins up the node and actually spins it up with a connection already. Is this correct? Now, how does the node know? How does know this is my orchestrator? I trust it.
He says I'm the node.
So by the way, Midlooker, he built big parts of Braid. Oh yeah.
Thank you very much. So basically, why it doesn't have the secret, but it works? That's the question, right? Okay. So basically, we modified OTP, and by the way, I made a pull request.
That wasn't the question.
No.
I explained that in the slides. The question was like, how does the node, when it started, know how to trust that the orchestrator? They can trust the orchestrator. So it gets spun off, and there is a connection already to the node.
Basically, yeah, because I don't know.
But does the node even need to trust the orchestrator?
Yeah, I mean,
is this even necessary?
No, it's more about us don't trusting the container. We didn't address this problem, so I don't know if we need this.
I'm not even sure we need this. Does this answer
maybe
your question?
Maybe later provide us with a use case, because it could be interesting. So,
I mean that goes more in the direction that you want to run you want to run code in untrusted infrastructure, which we didn't focus on. We basically build infrastructure you trust.
Trust us if you run on us.
Perfect. Take it to the Per and Luca and others from GRiSP will be in a booth over there, and hopefully you'll have a whiteboard and you can hash it out. Yeah. Any other? I think we have time for one short question. Okay. Sorry.
I noticed you showed some fairly static configuration files you deployed. Will there be more dynamic versions? That was a fixed hypercube 60.
So kind of like from the inside and from the outside. So actually on the flight here, I started to build a little link state routing protocol between Erlang nodes, because that's actually pretty nice on-flight exercise, so that the network from the inside can learn the actual topology. Because the config file only tells you this is my wanted topology, but the application might want to learn my actual topology if a node fails or whatever. And the other thing is the discovery, or for example, if you want to scale up, then you can say, okay, for every location, spin up one of those. So that's the plan. That, for example, if you want to aggregate some IoT data, you want to have an aggregator spun up everywhere on the edge, and you want this dynamically when the edge changes. So yes, we start with static because, yeah, you need to start somewhere, but in the end, everything will be super dynamic and just automatically crawl around the internet like a amoeba and take over everything.
All right, thank you, Per, and thank you, Luca.
Thank you.